Okay. Great, and it looks like we're live. So hi everyone at home. Welcome to another Wednesday evening at Cambridge University Astronomy. Here this week with Dr. Oliver Friedrich from the Kavli Institute for Cosmology. And he is going to be telling us all about how we do cosmology with large collaborations. So over to you.
Yeah, thanks very much, Matt. And yeah, thanks everyone for joining. And so let me just quickly share my screen. And there we go. Yeah, as Matt said, I'm going to tell you about work in a scientific collaboration and yeah, the kind of science case that we're looking for and what is exactly the workflow of how we're getting there. And in particular, I want to look at the dark energy survey. So this is a large observational program in cosmology, which I'm a part of, and yeah, which I obviously know most about. And yeah, the things I'm roughly going to tell you about is, first of all, I'm going to give you an introduction to the general science case. What are the kind of scientific questions that we are trying to get at within DES, which is short for Dark Energy Survey. Then I'm going to give you a little overview on the DES project and the collaboration. And then we're going to look at the DES workflow. So what are the different steps to get to the science case that I'm explaining in the beginning? And yeah, and then I'm going to briefly talk about some first results that we got from this. So yeah, moving on, just a little bit of background in cosmology. What we are going to look at today is really the transition from these between these two images that you see here. The one image telling us how the early universe looked like 13 billion years ago, and this would be this blue and reddish map that you see down here. And the other image showing you a galaxy cluster in today's universe. So each of these blobs, or most of these bright objects here, would be galaxies on the sky. And our understanding of cosmology and of the evolution of our universe can be roughly summarized by the following points. It turns out that up until about 380,000 years after the Big Bang, so this was approximately 13 billion years ago, the universe was filled by a hot plasma, so a mixture of matter and radiation with very high temperatures and very high pressure. And at that time, the universe was actually almost perfectly homogeneous. And yeah, and how we know about this is by what we're calling the cosmic microwave background. This is a background radiation in the microwave wavelength that reaches us from all directions of the sky, actually. And this is kind of, if you wish, the afterglow of this hot plasma in the beginning of the universe. And this bluish and reddish map that you see down here, so the first picture I talked about, this is exactly a map of this radiation on the sky. So if you look at this map, you see a lot of structures, but as a matter of fact, the contrast of this map is actually highly exaggerated. In reality, the relative fluctuations of this background radiation on the sky are just of the order of 10 to the minus 5. So this would be 0.001%. And this is actually quite intriguing if you think about it, right? We just look at the sky and in all directions, no matter where you look, almost the exact same intensity of microwave radiation is reaching us. And this is exactly how we infer and why we believe that the early universe must have been very, very homogeneous in order to emit this kind of homogeneous radiation or isotropic radiation towards us. And this is in quite stark contrast actually to what we see in the universe around us today. And now we're coming to this other image here, this galaxy cluster. If we look around us today, we see a very rich set of structures in the universe. This would be, well, galaxies. This would be clusters of galaxies, so very high concentration of galaxy density at some point on the sky. There's also voids, meaning that there's some regions in the universe which are completely empty of any observable objects. So you see, the universe today is actually by far not as homogeneous as we infer the early universe must have been. And so what is the dark energy survey about? What are the kind of scientific questions that we are trying to answer? You could roughly say what we are studying is the gravitational collapse on cosmic scales. And in other words, this really means that we are probing the transition from this homogeneous universe in its early phases to this highly evolved and structure-rich universe that we see today. And yeah, I've made this a little bit of a movie demonstrating this process, and this is what you see here. What you see in this in this movie is, in red, this would be density perturbations. So if the red line was exactly at 0 everywhere, then this would mean that that the universe would be perfectly homogeneous. So you see on the x-axis, you see some spatial coordinate, if you will. Yeah. So you can really think of this as like a slice through the universe. And here on the y-axis, you see the amplitude of density fluctuations. And you see, we start out in early times of the universe. So this is representing the universe at a redshift of 9.0. So this will be many, many billions of years ago. You see that the density perturbations are still quite tiny. But if we, as we turn on gravity, what's happening is that regions that are initially overdense, as for example, this lump that you see here, they will, by the power of their gravity, attract matter from its surroundings and become even more overdense and grow and eventually collapse and form these highly overdense peaks that you see here in the end, in, for example, this blue peak here. And such a peak would, for example, represent a cluster of galaxies. So this would be where you would find really many objects if you look at the sky. And in the contrast to that, if you look at initially underdense regions, as for example, this dip here, you will see that the surrounding overdensities will suck out even more matter from these initial underdensities, meaning that these initial underdensities will expand and become even more underdense. And yeah, this is also what you see here in this transition to the blue line. And it's really this transition to between these two lines that we are trying to understand. And yeah, it's a process that's mainly described by Einstein's theory of general relativity, plus some assumptions about unknown substances. But I'm going to talk more about that in a couple of slides. Now, yeah, the point is, my work is mostly theoretical, so a one-dimensional simulation like this is really the best I can do. But I don't want to leave you with just that. So I'm pointing you here to colleagues of ours, and actually also people in, from an institute that is also involved in the dark energy survey. And let me just quickly switch my windows. And yeah, these people have worked out basically the three-dimensional version of what I just showed you. And let me just quickly show that to you as well. You see the universe starts out as quite a homogeneous structure. And you see these initial overdensities collapse and form highly overdense objects. Here, for example, you would see these different bright objects would correspond to the halos of galaxies. And you see several galaxies will fall towards each other and even form clusters of galaxies. And in between these different overdense objects, you will actually see filaments of matter. And in between those filaments, these voids that I talked about initially. So yeah, and here you see the people at Stanford University that have put together this animation. Now, like I said, what we are trying to understand is really the transition from these tiny density fluctuations in the early universe to the highly evolved density fluctuations in the late universe. And yeah, this is equivalent to just testing gravitational collapse or the laws of gravity on large scales. And yeah, how can you how can you quantify this kind of growth of structures that we've observed? What you can do is you can, for example, measure the average amplitude or the variance of these density fluctuations. Yeah? For example, you could average both of these density fields on a certain scale. And this is what I'm trying to visualize here with these orange stripes that you see here. So you just choose a certain length scale, then you just average your density field on these scales, and then just measure the variance or the average amplitude of these orange stripes. Yeah? And yeah, this is exactly what I've done here. And you see, well, this orange density field corresponding to the early universe has variances as a function of scale. So here the x-axis would really be different widths of these orange stripes. And you see the amplitude of fluctuations in this early universe is significantly lower by more than a factor of 10 than in this late universe, as you can see here from these blue dots. And this is actually already pretty close to what we are actually doing in data. I'm going to show you a bit more about this at the very end of the talk. But this is very, very close to what the dark energy survey is trying to measure and to analyze. Now, the question is, or what you might ask yourselves is, given such a comparison, measuring the amplitude of fluctuations in the early universe and the late universe, what does this tell us, this kind of comparison? Or what are the scientific mysteries that we are trying to uncover with this? And I'm just mentioning one big thing here, which is what is the so-called dark matter? You know? And it actually turns out, if you look at this map, remember from the beginning, this would be a map of the cosmic microwave radiation on the sky. And the fluctuations, like I said, they are super tiny. They are 10 to the minus 5 in this map. And these fluctuations are actually too small to explain the rich structure that we see today. Yeah. So were we to go back, the actual amplitude of fluctuations in this cosmic microwave background map would be way smaller than I'm depicting here, and there's no way that normal gravitational forces could ever push these fluctuations up to the kind of levels that we actually observe today. And yeah, the reason for this is really, or a reason why these fluctuations are so tiny is in the very early phases of the universe, gravitational collapse actually could not really take place. And this is exactly because the early universe was filled with this hot plasma, and the radiation in that plasma was exerting such a high pressure to the entire plasma that density fluctuation simply couldn't collapse. You know? But the point is that this only holds for standard matter, so matter that would be comprised of protons and electrons, because it's these kind of particles, since they have electric charge, they will couple to the radiation in the plasma and will also take part in the pressure of the plasma. But there is another component of matter, or at least we think there is, which is the so-called dark matter. And actually, we think that about 80% of all the matter in the universe is made up of this mysterious substance, which, like I said, we call dark matter. And this substance actually only interacts gravitationally with everything else. It doesn't interact with light, and this also means it doesn't interact with the radiation in the plasma. And this means that it doesn't feel the pressure of the plasma, and dark matter perturbations can actually collapse. And this way they can, if you will, they can get a head start on the plasma and already start to form fluctuations. And now you might say that this is kind of a cheap trick, right? We observe this discrepancy, and then we just invent a mysterious substance, and that's solving the issue. But at this point, I should say, this idea of dark matter was not invented to explain this problem. It was invented to explain other observations, for example, the rotational velocities of galaxies, or also the velocities with which galaxies move inside galaxy clusters. So this whole concept of dark matter was really invented to solve an entire different problem. And it just turns out that afterwards, once these kind of comparisons were made, it also solved this problem. You know? So in that sense, you can see this as kind of a, it's actually an argument in favor of the dark matter paradigm, if you will, that it also helps to solve this kind of discrepancy. Now, so far for the science case of the dark energy survey, yeah, like I said, it's studying the evolution of cosmic structures, and especially we want to. So these kind of comparisons roughly have already been done like 10 years ago, 20 years ago. Yeah, so people knew that you also need dark matter to explain this transition from the homogeneous universe to the inhomogeneous one. But the point with the dark energy survey is really we want to study this process now really precisely as a function of time, really map how structures grow at different times, and via this find out more about this dark matter and its properties. So this is really one of the science cases, if you will, of the dark energy survey. Now, what is the dark energy survey? The Dark Energy Survey, or DES, is a collaboration of, by now, actually more than 400 scientists from 25 institutions in 8 countries all over the world. And yeah, I've just placed little stars here on all the countries that are participating in this project. And yeah, let me just name them. It's Australia, it's Brazil, it's Spain, France, the UK, Switzerland, Germany. And yeah, I've allowed myself to make the star of the US a little bit bigger, simply because there's really lots of institutions in many states of the US that are also participating in this. And yeah, what we're doing is together we operate a 4-meter telescope, the so-called Victor M. Blanco telescope at the Cerro Tololo Inter-American Observatory in Chile. And we also jointly analyze the data that is taken by that telescope. And yeah, ultimately the goal is to measure the positions and shapes of more than 300 million galaxies on the sky. And overall, the Dark Energy Survey is going to span 5,000 square degrees on the sky, so an eighth of the entire sky. And yeah, reaching to distances of really billions of light years away from us. And yeah, as you know, since light travels at a finite speed, looking billions of light years away means also that we look billions of years back into the past of the universe, right? And this is exactly where this kind of where we can see the evolution of the density field, which I mentioned before. You know? And yeah, next, let me just show you a picture from one of our collaboration meetings. So this is not all the 400 people, but yeah, here you see a bunch of them. And yeah, how would you actually organize such a large collaboration? Yeah, there's really lots of science cases. Yeah, what I mentioned in the beginning, just studying the amplitude of fluctuations is really just one of them. It's the major one, but really just one. And there's many different scientific working groups working at different aspects of the data at on different scientific questions. Each working group would also put together task forces, which consist of even smaller groups of people focusing on particular problems and solving them. And yeah, communication for us is, well, mainly via email. Sometimes these collaboration meetings, well, not anymore, to be honest, as you may know or may have guessed. There's Zoom meetings, and well, there's lots of communication via Slack, which is something like you can think of this as WhatsApp for businesses. And the point here is really that these kind of working groups within which we are organized, you can really think of them, even individual working groups would actually span different countries and different institutions. So it's not like, I don't know, the working group on galaxy evolution is just situated in Germany and some other working group just in the UK or something. Each working group will really consist of a vastly diverse and different group of people. And this really means that these kind of online communication channels are our main form of communication, which actually for us, to be honest, made it really easy to transition to this whole lockdown situation, because this was our communication anyway. Just having these Zoom meetings and emails and Slack. So this is roughly how we organize ourselves. And so what I want to show you now is, so in the beginning, I introduced you to this major science case of the dark energy survey. But now on the next couple of slides, we're going to look at really individual steps of that, yeah. And yeah, see how do we actually get from the data to this kind of analysis. And yeah, but before we move on, for those of you who are familiar with the Institute of Astronomy in Cambridge, there's 2 members of that institute on this picture. So yeah, if you have fun looking for them, then please do. Now, the DES workflow is well, it's quite a long one, consisting of many different tasks. And this is exactly why we need such a large group of people, and have to organize them in lots of different working groups. Yeah, but the DES workflow really starts with the telescope, obviously. You have, somebody has to be here and has to operate the telescope pointed at wherever in the sky we want to take our next images. Yeah, this is, to be honest, I don't know too much about that process. This is really the problem of working in such a large project. It's hard to keep the overview of what's going on, but this is certainly the first important step. Yeah? Now, step 2 would actually be understanding the camera and the images that we're taking from the telescope. And here you see an image of the what we call the dark energy camera, or DCAM. And this is actually, from its technology, not too different from, say, the cameras that you would have in your cell phone. It's a so-called CCD camera. And actually, there's many CCD chips. So you see here 70 chips overall. And so the telescope will direct the light coming from the sky towards these chips. And in order to interpret the images that you then take with this camera, you really have to understand the different properties of these chips. So, for example, the sensitivity of the camera towards light will really vary from chip to chip. Within each chip, there will be, say, pixels that are broken. There are really subtle effects, like if there is if there is a lot of light coming into one pixel of one of these chips, then what will actually happen is, it's almost as if you have a glass and you pour it too full with water. There will be an overflow, and some of the charge building up in that particular pixel will actually blur to the surrounding pixels. And this is a problem that has to be dealt with, for example, in order to understand what our images are really telling us about the objects that we see. So yeah, there's lots of really complicated work going on with that particular step. Step 3 is, once we have the images and understand the quality of the images, find galaxies and other objects that we're interested in. Yeah? And then once you have these objects, once you have a catalog of these objects, determine properties of these objects. Yeah? Determine how far away are they from us. Yeah? This is a super complicated problem, to be honest, because, well, we are looking at the sky and it's just a 2-dimensional surface. Yeah, how do you even know of one particular object on that surface, how far away it is? This is very complicated and mainly uses colors of galaxies. As you may know, as the universe is expanding, it's actually also expanding the wavelength of light. So light from very distant galaxies is looking redder than light from not so distant galaxies. And this is the so-called redshift. And yeah, this is mainly changes in the colors of galaxies are being used to determine how far away they are from us. but also characterize the shape, the ellipticity of galaxies. All these kind of things are important for the analysis that are to follow. And then we're coming to step 5. Once you have these objects, you want to use them to create a map of the universe, if you will. Yeah. And this is really where I'm attempting a tiny live demonstration. So yeah, bear with me. I hope this all works out. So first of all, let's just look at data that might be coming from this kind of such an analysis. At some point, so for people like me, for basically the working groups I'm involved in, we wouldn't know too much about all these other steps that would be going on before taking the data, understanding it, and the quality of the data. We would mainly work with finished data products. And this would be as trivial as it sounds, just a table, for example, like this one. And what you see here is just from a certain subset of the galaxies observed by the Dark Energy Survey, a table where in each row it tells you the right ascension and declination of the object. So this would be its position on the sky. It tells you the redshift of the object. Like I said, this is this effect caused by the expansion of the universe, expanding also the light being emitted from galaxies. And this you can actually use as a distance variable, if you will. So the redshift tells you how far away an object is. And these redshifts are only determined to a certain accuracy. So for example, there would also be the redshift uncertainty. So you have this kind of catalog. And now let's try to make a map of the universe. So yeah, this would just be a tiny bit of computer code written to load this kind of data. So yeah, let's load in the data file. Then let's choose a certain range of redshifts to single out galaxies in that range. So yeah, here I'm taking redshift of a redshift interval of 0.6 to 0.65. So this really means that I'm just going to single out a certain subset of all the galaxies that are in a certain narrow interval of distance towards us. Yeah? So these galaxies will all live in a narrow shell around us, if you will. Yeah? So let's just single them out. And yeah, now we can just plot their positions on the sky. And let's do that. And yeah, this is what you get. This is now a map of this particular shell of the universe. And you can really see here already the kind of structures that I talked about in the beginning, right? You would see, for example, there's very strong overdensities where these galaxies are clustering quite strongly. So for example, you might see a very strong overdensity here. There's also one here. On the other hand, there is also underdense regions, these cosmic voids. For example, this looks like there might be an underdensity here. But even here, things are actually quite tricky. What you have to understand is what you see here might not be 100% identical to the actual density field in the universe, because what also can happen is we are, well, first of all, the Blanco telescope is immersed in Earth's atmosphere, right? So it could simply be that when the people operating the telescope were observing this particular piece of the sky, it could just be that the thickness of the atmosphere was worse on that day. So, for example, maybe the telescope was just observing closer to the horizon, meaning that the light from the galaxies would have to travel farther through the atmosphere, and this would actually mean that less of the light of the galaxies would have reached us. And so this might be just an artificial underdensity caused by these kind of observational effects. Yeah? And so even here, you really have to understand the kind of observational, the technical messiness of this whole process in order to interpret this map. But yeah, let me just say that these kind of things have been dealt with, so you can be quite sure that most of the structures that you see here are actually real. And So just to make a little bit of a comparison, or just to convince you that what we are seeing here is not just a random distribution of points. Let's just distribute the same amount of points just randomly in that same area on the sky. So that's what we're going to do here. So this would just be a field of just random points. Yeah? And yeah, you can clearly see there's much less features and much less structures in this random set of points than you see here up in the real physical density field. Yeah? So these kind of clusterings are not just a chance alignment of these points. It's really, there's a significant overdensity in the cosmos at this location. And yeah, well, now we have this kind of map of the universe. And like I said, here we have singled out really just a narrow range of distances. But these kind of maps we can really do at a whole set of these ranges. So we can really see how the structures of the universe get more and more pronounced over time. And yeah, with that, let's go back to the slides. And yeah, this brings us to the last two steps, really. Now you have to measure how the fluctuations grow. So very roughly speaking, you make these kind of maps that we just saw, you make them at different intervals in redshift. And for each of these intervals, you measure again, just the amplitude of fluctuations. Yeah? Very similar to what we did at the very beginning, right? With this kind of 1D simulation. And then you do this for a range of different smoothing scales on the sky. And this is quite literally what I'm showing you here. This is now a figure from our first real big scientific publication. This was actually coming out 2018 already. It just took a while to get it published in a real journal. This is why you see the 2020 here. And this is really telling you for 5 different ranges in distance. Yeah. Remember, in that map that we just created, we singled out a particular distance of galaxies, or galaxies in a particular distance range. And in our main analysis, we really looked at 5 different distance ranges. In these 5 different distance ranges, we create a map of the universe and measure the amplitude of fluctuations as a function of scale. And then this brings us to the final step, step 7. Now, compare this to theoretical models. Yeah? So the points that you see here would be the measurements in our actual data. The line would be theoretical predictions. And fitting these lines to the data now allows us to understand the growth of structure as a function of time. Now, before I say a few words about what the theoretical results are from this comparison, let me just emphasize here that this is really vastly simplified. Yeah? First of all, I should say we don't just use the positions of galaxies. Yeah, so we don't just make a map of and just placing galaxies on the sky and analyzing this map. There's quite a lot of more things that we do. For example, we also analyze the shape of galaxies, because it turns out there's an effect called gravitational lensing. Basically, any very massive object, or the gravitational field of any massive foreground object, will act as a lens to the light of galaxies behind that object. And this, if the light of a background object is passing this gravitational field and this kind of gravitational lens, then the image of that object, that background object, is going to be distorted. And this distortion actually measures the mass of the foreground object. Yeah. We by far don't have enough time to talk about this in detail. But I think this recent talk that we also had in one of the open evenings by Naomi Robertson contains an introduction to that as well. So if you weren't around for this, I really recommend, and you're interested in this, I really recommend you check out Naomi's talk. And yeah, for example, another very important thing is working in these kind of big groups of hundreds of people. There's actually an interesting problem, which is the so-called confirmation bias. Just a one-sentence summary of what confirmation bias is. if you have such a large group of people working on a project, then mistakes will be made. Yeah? So for sure, in our analysis, there are some errors. It's unavoidable. Yeah? Now, if you have a certain theoretical prejudice on what the outcome of your experiment should be, then this is actually a problem, because imagine in our analysis there are 10 mistakes. Yeah? And then we do our study, we do the comparison, the kind of comparison that you saw here, and look at the results, and we don't like the results. Then what's going to happen is our entire collaboration, all 400 people, is going to get back to their codes, to their analysis machines, and are going to look for errors, what has been going wrong. And then we come back to the Zoom conferences, and we have found 5 errors. Okay, we fix the errors, we redo our analysis, and now the result is perfect, is exactly what we expected and wanted to see. Yeah? But what we of course didn't see is that there's 5 more errors in our analysis which we didn't fix, and had we fixed them, the result would have still been off from our prejudiced expectations. Yeah? And this is a really hard problem to deal with, and this is what's called confirmation bias. And there's a technique called blinding. Yeah, I won't go into much more detail on this, but also there has been a video from our Astronomy on Tap series where I talked about exactly this. So if you want to hear more about this blinding mechanism that we apply to avoid this confirmation bias, yeah, please check out this video as well. Now, yeah, moving on to first results here. And here I'm showing you now results from the analysis of our first year of data. And just to remind you, what we want to compare is what we want to understand is the transition from the early universe, which was almost perfectly homogeneous, to this evolved and structure-rich universe at today's times. And what you see here in this figure is redshift on the x-axis. So this you can just think of as a time variable. This is time. And on the y-axis, you see now again the variance of fluctuations now just for one smoothing scale. You know? And I'm showing you 2 things here. First, in the blue, I'm showing you results from another collaboration and another measurement, the so-called Planck satellite and the Planck collaboration. This is a project where also Cambridge has been strongly involved. And this was exactly the project or the collaboration that created this map of the early universe that I showed you in the very beginning. And yeah, the Planck team has measured the amplitude of fluctuations from that map and inferred now also the real amplitude of fluctuations, not just of the plasma, but also of the dark matter. If you remember from the beginning, the amplitude of the fluctuations in the plasma are actually much smaller than the real underlying matter density fluctuations of the dark matter. So in blue, I'm showing you here the dark matter density fluctuations. And Planck has measured those here at very early times at a redshift of roughly 1,000. And I'm using a theoretical model now to extrapolate how that would have evolved over time. And this is what you're seeing here in this blue band. Now, this is just a theoretical extrapolation of this early universe result to late times, to our ages of the universe. But you could also, of course, instead of doing this extrapolation, you could just look at the sky and just measure what the amplitudes are, right? And this is exactly what the dark energy survey is doing. And this is what I'm showing you here in the orange band. So this would be the amplitude of fluctuations as a function of time as seen by the dark energy survey, you know, from the galaxy distribution, but like I said, also from the shapes of galaxies, actually. And yeah, you see, there seems to be a sort of discrepancy here between the two. So it seems like structures have not grown as fast as our theory of general relativity plus our assumptions on dark matter and other components of the universe actually predict. Now, I should say the discrepancy between the two actually looks a bit exaggerated here. So the width of the 2 bands show you roughly the observational uncertainty that we have on this amplitude. And yeah, this figure looks a bit exaggerated. mainly because I have had to project the data from the two surveys in weird ways in order to be able to show this simplified comparison. So in reality, the discrepancy is not as high as indicated here, but it is somewhat discrepant. So there seem to be some slight hints that maybe we don't understand gravitational collapse on these large scales and cosmic times as well as we thought. And yeah, this brings me to the end of the talk. Yeah, what's on the horizon? Like I said, the slide that you saw before is really just the first year data of DES. And ultimately, we are going to analyze 6 years of data, so much more area than what I just showed you, and also deeper into the history of the universe. And right now, we're almost done analyzing the first 3 years of data. So this should significantly improve the power with which we can do this comparison that you saw here, right? And yeah, from that, we are really hoping to get exciting new insights into what's going on there. What's this slight discrepancy that we're starting to see in between early and late universe? And yeah, this is going to help us understand better the properties of these mysterious substances like dark matter that we have to assume. And yeah, just it's going to help us test our understanding of gravitation on cosmic scales in general. And yeah, this is something really to look forward to. And yeah, I'm closing here. Thanks very much.
Cool, wonderful, Oliver. Thank you so much. That's really fascinating stuff. It's really nice to see like the nuts and bolts behind the science, actually how we do research on like a day-to-day basis. So comments and questions coming in thick and fast, which I like. So if you have a question for our speaker, you can put them down there in the YouTube chat to the right. We'll kick off with this one, first of all, from Nuno, who wants to know, can individual particles have halos of dark matter? So in the same way that entire galaxies have halos of dark matter, like how small do the scales get?
Yeah, I don't think that individual particles would have a halo of their own, mainly because well, actually, dark matter itself is also, or at least we assume that it consists of particles. So for individual particles to have dark matter halos would mean that one individual particle would have to capture these other particles. And I think on these small scales, just the velocity of the individual particles would be too strong to actually have them capture each other, if you will. But well, I mean, there are some. So for example, right now in the simplest paradigm, what we are assuming is that individual dark matter particles don't interact with each other as well, or rather, they only interact gravitationally. But there is also theories out there telling us that there can be, for example, chemical reactions between dark matter particles. So in that sense, you could wildly speculate and say maybe there's chemical compounds of dark matter particles, and then in that sense they would be able to capture each other and then cluster on the particle level as well. But that's very speculative.
So another question about dark matter. Someone's wanting to know whether this research rules out certain dark matter candidates, like brown dwarfs, for example.
Yeah. So our research doesn't necessarily rule out brown dwarfs, but if I understand correctly, then there is actually related analysis that rule out these kind of candidates. So this gravitational lensing effect that I was talking about, you would actually see this. So one way how people are testing for this is, for example, they look at the Andromeda galaxy, which is one of the closest galaxies to our own Milky Way galaxy. And between those galaxies, we know between the Milky Way and the Andromeda galaxy, we know that there is lots of dark matter in between them. If all that dark matter would consist of these compact objects such as brown dwarfs, then every once in a while such a brown dwarf would pass by a star in the Andromeda galaxy very closely, and then you would see this gravitational lensing effect. So you would see suddenly the star in the Andromeda galaxy flicker because you have this compact object going in front of it. And this is something that people have actually been looking for, and that people haven't found in the amounts necessary to explain all the amount of dark matter. And this is really an argument in favor of dark matter really consisting of this on this diffuse gas of particles.
So we have a question from Julia, who first of all is very impressed with the collaboration across different nations, but wants to know how you decide who does what in the collaboration.
Yeah, this is a real tough problem. Let me just quote a colleague of mine. Yeah, he once said, "A large collaboration is not so much like a beehive, but more like a sack of fleas." And I don't totally subscribe to that notion, but there is some truth to it in the sense that you shouldn't think of it as like a company, right? So we have some sort of management structure, and there are senior people coordinating stuff. But rarely ever is there somebody like giving an order, now you have to do this, now you have to do that. the it's mainly, it organizes itself, if you will. The point is, what I told you about is really just the main science case, studying these amplitude of fluctuations as a function of time. So this is what 15 years ago or so the founders of DES have promised the funding agencies, and this is what we are going to do. And this is our core project, and this is what everybody works on. By being engaged in this large project and helping push our main objective forward, we also help our own goals, if you will. So, for example, I myself also have side projects that are not directly related to this main objective that I just told you about. But these kind of side projects also rely on having this well-characterized good data from the main project. So a lot of the motivation for people just comes from pushing ourselves as a whole forward. And then we can all, for our individual projects that we are interested in, also benefit from what's coming out there, because this main project is going to produce such an exquisite data set that many other science cases are going to profit from this. So this is where kind of the self-motivation is also coming from, to an extent. And yeah, apart from that, it's to some extent also seniority, right? Some senior or experienced person, I should say, is going to lead a working group, and he's going to be tasked with finding out what kind of issues have to be tackled, and then he's going to find people or ask around for people to volunteer for tasks, and then regularly in these teleconferences we would talk about it. So it's really it's a very flat management structure, if you will.
Okay, thank you. And one final question. Do you use any kind of advanced techniques like artificial intelligence or machine learning to deal with these massive complex data sets?
Yes, totally, yeah. So just to give you one example, I said at some point that that we are trying to determine how far away a galaxy is, and that's actually quite complicated to determine. What we do is, for each galaxy, we measure each galaxy in 4 different optical bands. So for each galaxy, we have its luminosity in 4 different wavelength ranges, or in 4 different colors, if you will. And from these 4 different colors, you would try to infer the redshift, and then from that, the distance. But what people have been applying in DES is also just training a machine learning algorithm. So instead of, say, trying to theoretically understand what the 4 colors mean in terms of distance, you can also just try to train a machine that directly, you feed the machine the 4 colors of a galaxy, and then the machine tells you how far away it is. So this is methods that have been successfully applied, but there's also other methods. There's methods, for example, to characterize the shape of galaxies. You might use machine learning, or there's really many things, even at the theory level, actually. This may be interesting to know. These kind of theory lines that you saw here. So not in this particular analysis, but in an analysis where I'm involved in as well, for example. Sometimes our analytical modeling is very slow. But if you have certain parts of your theoretical calculation which are well understood, then you can just train a machine to carry out this calculation, and it may be much faster. And you can actually even boost your analytic modeling using machine learning, if you will. So yeah, we are using these kind of techniques as well.
Cool, amazing. Well, thank you so much, Oliver, and thank you to everyone listening at home. I hope you enjoyed it. Thank you for asking very good questions. As always, we will be back next week with another talk from one of our fantastic speakers. So yes, see you guys next week.
Thanks very much.